3.11 Linearization and Differentials. The outline of this video is as follows. We will discuss how to approximate a complicated curve with a simple straight line, a powerful idea known as linearization. I will begin by introducing the core concept, then provide a formal definition and work through several examples to make it concrete. From there, we will develop a related tool called differentials, which allows us to estimate how a function's value changes when its input changes by a small amount. Because this is an approximation, we will also analyze the error involved to understand its limitations. Next, I will show you how these concepts provide a solid foundation for proving the chain rule, one of the most important rules in calculus. We will conclude by exploring the broader topic of sensitivity to change, which is a key application of these ideas in many scientific fields. One of the most powerful ideas in calculus is that we can approximate complicated functions with simpler ones, making them much easier to analyze. A smooth, differentiable curve has a special property. If you zoom in on any single point, the curve starts to look less curved and more like a straight line. This straight line is the tangent line at that point, and because it stays so close to the curve in that small region, we can use its simple equation to estimate values. For example, as we magnify the view of the graph y equals x squared around the point 1, 1, the parabola flattens out and becomes almost indistinguishable from its tangent line. The essential idea to remember is that any smooth curve behaves locally like its tangent line on a small enough scale. Let us explore how we can approximate a complex function with a simple straight line, which is a powerful tool in calculus. This process is called linearization. For this to work, our function f must be differentiable at a point we call the center, x equals a. The linearization, which I will call L of x, is simply the equation of the tangent line at that point. L of x equals f of a plus the derivative f prime of a times the quantity x minus a. This means we start at the known point on the curve and then follow its slope for a short distance. For example, if you zoom in far enough on any smooth curve, it starts to look like a straight line, and that line is its linearization. The key takeaway is that near the center point, the value of the linearization L of x gives a very good, and much simpler, estimate for the actual value of f of x. Let us now apply the linearization formula to find the best linear approximation for the function f of x equals the square root of 1 plus x, centered at x equals 0. To build our approximation, we first need two key values at our center. The function's value, f of 0, is the square root of 1 plus 0, which is simply 1. Next, we find the derivative, which is 1/2 times the quantity 1 plus x to the power of negative 1/2. Evaluating the derivative at 0, f prime of 0, gives us 1/2. Now we can assemble the linearization L of x, which equals f of 0 plus f prime of 0 times x. Plugging in our values gives us the final result. L of x equals 1 plus 1/2 times x. This simple line serves as a very good approximation for our original square root function, as long as x remains close to 0. The usefulness of a linear approximation depends entirely on how close we are to its center point. Using our recent approximation, where the square root of the quantity 1 plus x is about 1 plus the fraction x over 2, we can see how this works. This formula is centered at a equals 0. When x is very close to 0, such as x equals 0.05, our approximation gives 1.025, which is extremely close to the true value, with an error of less than 4/10,000ths. However, as we move away from the center, the accuracy degrades significantly. If we try to evaluate at x equals 2, the linearization gives a result of 2, while the true value of the square root of 3 is about 1.732. This demonstrates that a linear approximation is only reliable in a small neighborhood around its center. Let us apply our linearization technique to a trigonometric function, which is a very common tool in physics and engineering. We'll find the linear approximation for f of x equals cosine of x, centered at x equals pi over 2. First, we need the derivative, which is negative sine of x. Next, we evaluate both the function and its derivative at our center. The cosine of pi over 2 is 0, and the negative sine of pi over 2 is negative 1. Plugging these values into our standard linearization formula gives us L of x equals 0, plus the quantity negative 1 times the quantity x minus pi over 2. For example, this simple line allows us to estimate the cosine of an angle very close to 90 degrees without using a calculator. The important result is that near x equals pi over 2, the complex cosine curve can be accurately approximated by the simple straight line L of x equals negative x plus pi over 2. Now let us look at a particularly useful linear approximation that simplifies calculations involving powers and roots. This powerful shortcut is the result of applying our linearization formula to the function f of x equals the quantity 1 plus x, all raised to the power of k, specifically at the point where x equals 0. The approximation states that for values of x near 0, the quantity 1 plus x to the power k is approximately equal to 1 plus k times x. This allows us to estimate complex expressions with simple arithmetic. For instance, the square root of 1 plus x, which is the quantity 1 plus x to the power of 1/2, becomes approximately 1 plus 1/2 times x. Another example is 1 over the quantity 1 minus x, which is 1 minus x to the power of negative 1. Its approximation is simply 1 plus x. The key takeaway is that this formula transforms a difficult power or root into a simple linear expression, as long as x is small. Now I will introduce two new variables, called differentials, which allow us to treat the notation dy over dx as a true mathematical ratio. For any differentiable function y equals f of x, we start by defining the differential dx as a new independent variable, meaning we can choose its value. Then, we define the dependent differential dy with the formula dy equals f prime of x times dx. So, the value of dy depends on both the point x and our choice of dx. For example, if y equals x to the power of 5 plus 37x, its derivative is 5x to the power of 4 plus 37. The differential is therefore dy equals the quantity 5x to the power of 4 plus 37, all times dx. If we plug in x equals 1 and dx equals 0.2, we find that dy is 42 times 0.2, which equals 8.4. The main takeaway is that the differential dx is simply the function's derivative multiplied by the differential dx. Now I want to connect the differential dt to a clear geometric picture, which shows why it is so useful for approximations. When our input x changes by a small amount, which we call dx, the function itself changes by an amount called delta y. Looking at the figure, you can see this is the true vertical change along the curve. However, if we follow the tangent line for that same horizontal step dx, the vertical change along that straight line is what we call delta L. The definition of the tangent line's slope means that this change, delta L, is exactly equal to the derivative f prime of a times dx. And since we defined the differential dt to be that very same product, it means dt is precisely the change in the linearization. Do not confuse the differential dy with the actual change delta y. One is the change in the tangent line, while the other is the change in the function itself. The essential idea is that the differential die represents the exact change in height along the tangent line for a given step dx. Let us see how we can use the differential as a practical tool for estimating the actual change in a function's value. We need to distinguish between the true change, which we call delta by, and our linear estimate, which is the differential dey. The true change is the function's value at a plus delta x minus its value at a. Our differential estimate dy is simply the derivative f prime of a times dx. The core idea is that when the input change is small, we can set dx equal to delta x, and the easily calculated dy becomes a very good approximation for the true change delta y. This gives us a powerful formula. The function's value at a nearby point is approximately equal to its value at a, plus our differential estimate dy. For example, to quickly estimate the increase in a circle's area when its radius grows from 10 to 10.1 meters, we can use the differential dA instead of calculating the more complex true change. The key is that dy is the simple change on the tangent line, which approximates the actual change on the curve. Let us use a differential to estimate the change in a circle's area when its radius grows, which is a very practical application of this tool. First, we need the differential of the area formula, a equals pi times r squared. The derivative, a prime of r, is 2 pi r, so the differential dA is equal to 2 pi r times dr. Now I will substitute the given values. The initial radius r is 10 meters, and the small change in radius, dr, is 0.1 meters. This gives us an estimated area increase, dA, of 2 pi times 10 times 0.1, which simplifies to 2 pi square meters. To see how good this estimate is, we can calculate the true change, delta A. The new area is pi times the quantity 10.1 squared, or 102.01 pi. Subtracting the original area of 100 pi gives a true change of 2.01 pi. Our estimate is incredibly close to the exact value, demonstrating that differentials provide a fast and accurate approximation. Now let us analyze how well our differential estimate, DEF, approximates the true change, delta F. Understanding the error is crucial, because it confirms that our linear approximation becomes extremely accurate for small changes in our input. We can write the true change, delta F, as the sum of our estimate, which is f prime of a times delta x, and a small error term. This error term is itself a product of two quantities, an error factor we call epsilon, and our original change, delta x. From the very definition of the derivative, we know that as delta x approaches 0, the ratio delta f over delta x must approach f prime of a. This directly implies that the error factor epsilon must also approach 0. So the total error is a product of two small numbers, making it even smaller. The essential result is that the error in our approximation shrinks much faster than the change in x itself. Now we can use our precise definition of change to formally prove the chain rule, which is a cornerstone of calculus. We start by expressing the change for both the inner function, delta u, and the outer function, delta y, using the error term formulation we saw earlier. The key step is to substitute the expression for delta u directly into the equation for delta y, which connects the final output change back to the initial input change. After dividing by delta x to create the difference quotient, we take the limit as delta x approaches 0. As this happens, both error terms, epsilon 1 and epsilon 2, vanish, which elegantly avoids the problem of dividing by 0 that can occur in simpler proofs. This process leaves us with the derivative of the outer function times the derivative of the inner function, rigorously confirming the chain rule. The derivative gives us a powerful way to measure how sensitive a function's output is to a small change in its input. We can describe this sensitivity in three distinct ways, each having both a true value and an estimated value. First, the absolute change is the raw difference in the output, which we estimate using the differential df equal to f prime of a times dx. However, to understand the significance of this change, we use relative change, which compares the absolute change to the function's original value, f of a. For example, a $1 change in price has a much larger relative impact on a $10 stock than on a $500 stock. Finally, to make this comparison more intuitive, we can simply multiply the relative change by 100 to get the percentage change. The differential provides a fast and effective way to estimate all three of these important measures. We can now use linear approximation to uncover one of the most profound ideas in science, the equivalence of mass and energy. We start with Einstein's formula for the mass of an object moving at velocity v, which depends on its rest mass, m0, and the speed of light, circa. By applying our standard linear approximation formula where u equals negative v squared over c squared and k equals negative 1/2, we can simplify Einstein's equation for velocities much smaller than the speed of light. After rearranging the resulting expression to isolate the change in mass, which we call delta AEM, we multiply both sides by c squared. This final step reveals that the change in mass times c squared is approximately equal to the object's change in kinetic energy, or the energy of its motion. Because the speed of light is so large, this means a very small amount of mass can be converted into a tremendous amount of energy. This shows that mass and energy are fundamentally interchangeable. Let us bring together the main ideas from this section, which all center on the powerful connection between a function and its tangent line. We began with linearization, the technique of approximating a function near a point using its tangent line, which we wrote as L of x equals f of a plus f prime of a times the quantity x minus a. To formalize this, I introduced differentials, where dy, defined as f prime of x times dx, represents the exact change along that tangent line. The crucial insight is that for a small change in x, this easily calculated differential df qi provides an excellent estimate for the true, and often more complex, change in the function, delta y. This makes it invaluable for applications like estimating error propagation. Ultimately, this entire framework of differentials is what provides the rigorous foundation needed to formally prove fundamental results like the chain rule. To conclude, let us look at two review questions that apply our main tools of linearization and differentials. The first problem is a classic approximation task, where we will find the tangent line to the function f of x equals x cubed at the point x equals 2. We can then use this simple linear equation to estimate the value of 2.01 cubed and check how close our approximation is to the true value. The second problem shifts our focus to error analysis using differentials. Given a cube with a measured side length and a small potential error, we will use the derivative of the volume formula to estimate the maximum resulting error in the cube's calculated volume and find its relative error. Successfully solving these problems demonstrates how derivatives provide powerful methods for both local approximation and practical uncertainty analysis.